This conference
All
will
right,
now
can
be
everybody hear
recorded.
me? Talk
This
about today
conference will
is
now be recorded.
what we want to talk about today is Gage R&R. A lot of people are kind of confused, or maybe don't realize some of the benefits or the tricks of the trade for Gage R&R. So we're going to go through there. One of the things we're absolutely going to want to sort out here is the difference between gauge error and measurement error. Those are two totally different errors. I'm going to go through this fairly quickly so we can pack this all into the lunchtime. But the gauge error is the error that you have within the gauge itself. Measurement error is when you take a perfectly good gauge and use it wrong. So Gage R&R focuses an awful lot on the gauge error, and you can have a perfectly good gauge in a Gage R&R, and in its usage end up with bad data because you're simply using it incorrectly. So we want to go through some basics here just to build upon some basics. We might not have seen this for a long time. Some of us may not have seen it at all. A lot of it's in the AIAG books, but we want to go through this so we can build upon it. The first thing is measurement variability. The description of the measurement of variability is based on location, or the average data value that you'll get whenever you do a measurement, and the width, or the spread of the data from the average data value for the measured characteristic. So if you measure a characteristic over and over again, you won't get the exact same number every time. Well, what's the width of the variation that you are going to see? Those are the two things that we want to take a look at as a part of measurement variability. For most measurement processes, the total measurement variation is usually described as the normal distribution. Normal probability is an assumption for standard methods of measurement systems analysis. So remember that. It's an assumption for an awful lot of things, and it's not always true that it applies. There are, however, measurement systems that are not normally distributed. For example, measuring a unilateral form characteristic such as flatness or runout. So chances are, if you're using a measurement system that's measuring something that's not normal to begin with, it's quite possible that the variation you'll see in the measurement system itself is not going to be normal. When this happens and you assume normality, the normal-based method may overestimate the measurement system error. A measurement analyst must recognize the correct evaluations for non-normal measurement systems. We're not going to get into that today, but I'm just throwing that out there as one of the caveats that rubber stamping Gage R&R is not always correct way to handle the situation. So what is the effect of gauge error on data? A gauge with less measurement variance will generate measurements more closely that resemble the true value of the characteristic, which is what you want when you're trying to make decisions on a characteristic. Decisions made with poor quality measurements may imply that bad parts are good or good parts are bad, and may also cause overadjustment, which is something we're always trying to avoid. So what's discrimination? It's the amount of change from a reference value that an instrument can detect and faithfully indicate. It's also referred to as readability or resolution. The measure of this ability is typically the value of the smallest graduation on the scale of an instrument. If the instrument has coarse graduations, then a half graduation can sometimes be used. Most manufacturing, you won't want to go down that path, however. General rule of thumb is the measuring instrument discrimination ought to be at least 1/10 of the tolerance to be measured, or 10-to-1, or 1/10 of the process variation if used for process control. That's key. If you're going to use it to detect good or bad parts, it's 1/10 of the tolerance. But if you're going to use it to control a process, it needs to be 1/10 of the process variation. Generally, that would fall between the variation between your control limits. We also look at bias, and that's the difference between a true value that the average observed value and measurements of the same characteristic on the part, sometimes referred to as accuracy. The measure of the systemic error of the measurement system as it occurs all of the time. Now, what are the causes of bias? Well, essentially what you're looking at is that shift from the true measurement. Number one thing, the instrument needs calibration. Now, the interesting thing about calibration is some people will question, for example, do you calibrate a steel rule? That's often a trick question, but the answer is real easy. Yes, you do. You always check your gauges against the standard traceable to NIST. There could be wear on that rule that makes it, especially on the end, it makes it inaccurate. Just because you can't make an adjustment doesn't mean you can't calibrate, ever. Adjustment is just a bonus you have for some gauges that if you're out of calibration, you don't have to throw them away, but you have the ability to adjust them and continue to use them. Other causes of bias: worn instrument, equipment, or fixture, worn or damaged master, error in a master, improper calibration or use of a setting master, poor quality instrument, design or conformance, linearity error, wrong gauge for the application, different measurement method, setup, loading, clamping techniques, measuring the wrong characteristic, distortion of the gauge or the part, environment, temperature, humidity, vibration, cleanliness. A lot of people forget that if they're working in the realms of millions or microns. Violation of an assumption, error in the applied constant or application, part size, position, operator skill, fatigue, observation error, readability, and parallax. So what are the components of Gage R&R? We know that it's repeatability and reproducibility. Gauge repeatability and reproducibility is often referred to as Gage R&R. Some people call it MSA, but MSA is actually the group of all those things that apply to analyzing a gauge, not just the Gage R&R. So it includes things such as calibration, linearity, and stability, and so on and so forth. MSA, oh, see, I already knew that, and I already shared that. Gage R&R is a subset of the MSA. So what is repeatability? It's the variation in measurements attained with one gauge when used several times by one appraiser while measuring the characteristic on one part. Can one person repeat the same results that they previously got? This is traditionally referred to as within appraiser ability, and this is key. Within. This is often inherent variation or the capability of the equipment itself. Because if I'm using it over and over again and it's still getting variation, that's generally within that equipment, and that's what we're observing within. Repeatability is commonly referred to as equipment variation, or EV, although this is very misleading. In fact, repeatability is the common cause of random error variation from successive trials under defined conditions of measurement. The best term for repeatability is within system variation. I'll show you why in just a couple of minutes. When the conditions of the measurement are fixed and defined, fixed part, instrument, standard, method, operator, environment, and assumptions, this is the variation you will see. In addition to within equipment variation, repeatability will include all within variation from any condition in the error model. So when you look at poor repeatability, if you fail a Gage R&R and you're trying to figure out why you failed, and the repeatability is the problem, then what you do is you look for within types of error. For example, within part. Are you moving around a part instead of checking one part? Hey, if you are capturing roundness because you're not measuring the same place over and over again, that's not the gauge's fault. You don't want to include that as a part of your gauge analysis. You just want to know if that gauge can measure that characteristic. Within instrument, within standard, within method, within appraiser, within environment, violation of assumption, instrument design, wrong gauge for the application, distortion application. So when you have failed repeatability, you look for within types of errors. Reproducibility is the variation in the average of the measurements made by different appraisers using the same one gauge when measuring the characteristic on one part. Can one person reproduce the results that another person got? This traditionally is referred to as between appraisers variability. This is often found in manual instruments influenced by the skill of the operator. It's not true, however, for measurement processes where the operator is not a major source of the variation. For this reason, reproducibility is referred to as the average variation between systems or between conditions of a measurement. So when you have a failed reproducibility, what you're looking for is between types of errors. And again, the whole reason why you should be watching a Gage R&R is if it fails, you need to look for between and within types of errors. So the between types of errors is the average difference in measuring different types of parts. When you're watching the person handle the parts, are they difficult to handle? Between instruments, average difference using different instruments. Between standards, between methods, are the operators handling the gauge exactly the same way? Or are they handling it different, creating variation, causing a reproducibility error? Again, between appraisers, are they doing it differently? Between environment, did you do one during the day and one at night, and it was hotter during the day and cooler at night? Any violation of assumptions study, instrument design, operator training effectiveness is key. When you gave them the gauge, did you show them how to use it? Or are they on their own devices to figure out how to use it, and they come up with different ways causing reproducibility error? And then again, are they having difficulties handling the part? The approach is called crossed Gage R&R study because all appraisers will be measured, all parts presented in the study. So when you're picking what type of Gage R&R study you're doing, especially if you're in Minitab, you use the cross point. Gage R&R is the most important step for determining the appropriateness of a gauge to an application. That is the point of the exercise. Gage R&R tells you if that gauge is the right gauge for the application. If somebody says this gauge doesn't work, Gage R&R will prove whether it is the gauge to use or not just a off-the-hip conversation with somebody trying to use the gauge. It is the proof. Now remember this, all gauges are bad. All gauges are bad. None of them are perfect. They're all bad. However, this determines if the gauge is good enough. Even with all the badness in that gauge, all the error that it may have, is the error small enough that it's not going to affect its use? Because the point of Gage R&R is to determine if a gauge is appropriate for a particular characteristic, it has no time function. Of all the things in the MSA, once you've done your Gage R&R and said, yes, this gauge is correct, you're done. Now, sometimes you'll have people asking you to do annual Gage R&Rs, and there's virtually no value in doing an annual Gage R&R because there is no time function to Gage R&R. Again, if you've already determined it's the right gauge for the job, it's still the right gauge for the job tomorrow and the next day. If the conditions captured in the original Gage R&R were truly representative of the appraisers and the measurement process and have not changed over the period of time. However, observant customers have noticed that changes have occurred in the gauge system over time, and they were not validated with new Gage R&Rs. So, for example, you may have used very well-trained people when you did your first Gage R&R, and now the gauges are being used by temps. That is a significant change. You should have a Gage R&R that proves that people with a different skill set are capable of using that same gauge with the same success. So, they figured an annual Gage R&R will capture that when nobody's paying attention. But the fact is, there really is no time function to Gage R&R. MSA studies that do address changes over time are calibration, stability, and linearity. So if somebody says, well, the gauge worked great before, it seems to be a problem now. It's not the Gage R&R that's going to tell you what the issue is. You need to look at the calibration, the stability, and the linearity. Those have time functions. They change over time. Those should be telling you whether that gauge is still functioning correctly to the initial function that it had during the Gage R&R. And if it does, then it should be fine. Gage R&R will identify the effects of gauge error and operator error are small enough to be acceptable or too large to be of any value. Again, all gauges are bad, but if these errors that occur with that gauge are small enough, then it could be acceptable. It will not tell you whether the gauge is being used wrong. So for example, if you're measuring a circular feature and you only measure one diameter, instead of measuring around the part and picking up the influence of roundness, then if you see variation in your data, but the data is from roundness and not from variation over time, well, then you're just using the gauge wrong. That will not get caught in a Gage R&R. Gage R&R require a large enough sample of data to be statistically significant. The sampling must be representative. It must be representative of the part to be measured and representative of the users of the gauge. Now, this is really key. The parts must be representative of what you're going to measure. A lot of people say, well, I'm going to use this gauge. I'm going to use gauge blocks because it'll make it really easy because I can get the variation I can need from a gauge block. But if you're measuring a part that is awkward, has a cantilevered load, and the operator has a difficulty putting the gauge on that part, you're not going to capture that by measuring gauge blocks. So it's not going to be an accurate representation of the error that that gauge is going to have trying to measure the actual part. So the parts being measured should be representative of the part to be measured. The people using it should be representative of the users of the gauge. So generally they should be shop floor personnel if the shop floor personnel are going to be using that gauge. They shouldn't all be gauge techs and engineers because they have a different skill set when operating those gauges, and it would not be an adequate Gage R&R for the usage of the gauge on a day-to-day basis. Now, some people like to make Gage R studies generic by measuring gauge blocks or pins instead of actual parts, but it misses collecting the possible gauge error from handling unwieldy parts while trying to measure them. A sample parts must be selected from the process and will represent the variation of process it will see over its entire life. So if you're getting 10 parts, what those 10 parts are supposed to represent is the variation that that process will see over its entire life. The problem is, generally, you haven't made that much variation yet when you go to do your Gage R&R, and that creates a problem in getting an accurate Gage R&R. Collecting parts to present to the study, and this is all how I refer to it. Those 10 parts, whatever they are what you're going to present to the study, and they are to represent the process variation. You're going to use that variation between those parts to represent your process variation. If they don't, then you're going to get incorrect data coming out of your Gage R&R. The sample part data is used to calculate PV, or the part variation. And again, that's the expected part-to-part and time-to-time variation for a stable process. So generally, those parts should be varied within, for example, your control limits if you're doing an SPC on that particular characteristic. If the process variation is known and its value is based on 6 sigma, then it can be used in place of the total study variation and calculated from the gauge study data or the part variation presented to the study. Now, this is very handy because most software now accommodates this approach. In Minitab, it's even strongly recommended. You use historical standard deviation. Now, why is this handy? Because that way you don't have to worry so much about the variation in the parts that you're presenting to the study representing the variation. You're going to get it from the true process variation, plug it in as a function of the standard deviation, And now your study is going to be much more accurate when you're done. It's also important to mark the part and measure the part at the same location, because otherwise you are capturing within part variation, and it's not the gauge or appraiser's fault. So that variation should not be included in the gauge error analysis. In fact, within part variation should be part of your measurement technique that you use to eliminate measurement error, not a function of gauge error. So who's going to use the gauge? At a minimum, typical users of the various skill levels. That means if on your shop floor, those people that are going to be using that gauge are everything from a 15-year veteran to a temp or somebody just starting, then those skill levels should be included in the evaluation, because they all should be able to get adequate data. You can use one trained gauge technician as a part of the appraisal, and when that comes in handy is it will give you a better perspective of the effect of operator skill on the outcome. So if you have one trained gauge technician using it and the other two are typical of the variation you see on the shop floor, and you see that the trained gauge technician has very little variation, but the others have a lot of variation, boom, right there you know that you have an appraiser issue, that gauge is very sensitive to gauge skill level, and you'll have to deal with that either by bringing up the skill level of the people, including future people, in order to pass that Gage R&R and make that gauge effective for measuring that characteristic. How do you conduct a study? First, you obtain a sample of at least 5 parts that represent the actual or expected range of process variation. You will never get a Gage R&R to work if the parts are identical. One of the key things that the Gage R&R is trying to figure out is if you have 5 parts within the process variation, can you tell them apart? If you can't, then it's not enough resolution in that gauge to find out what's going on in your process. However, if your process has more variation, the parts that you presented to the Gage R&R, then it's certainly you'll never know whether or not that gauge is going to be working within that variation or not. It can't tell those parts apart if they're too similar, and it will fail. You want to mark the parts where they're measured so that you reduce any within part variation during the test. You prepare a randomization plan to perform the test, and do not allow the operators to see the previous data. Oftentimes people give them a sheet and they can see what they wrote last time. That will guarantee bias error. Guarantee it. A different bias than what we discussed before. This bias is the person trying to get the correct value in quotes. So if I see that the last time I got 1.35 and this time I get 1.45, I say, well, maybe I'm doing something wrong and mess with it. And oh, now I got 1.35. That's bias. It's assuming that the first value is correct and I'm trying to reproduce it. However, if I have a blank sheet in front of me each time, I'm going to write down whatever I get. And that's what's going to happen in real life. That is why you don't want to have that bias influence, so you give them a blank sheet every time. You calibrate the gauge, of course. We want to get any of that variation out of the way. You have the randomization plan. Train the operators on how to use the gauge. Let's be fair. Unless you don't plan on training operators on how to use the gauge, and you get a real evaluation when a new operator uses it. But I think to be fair to the appraisers, you ought to at least show them, okay, this is how you use this gauge. And you should be able to do that in the future when you have a new operator using that gauge. You follow the randomization plan, which is important when using ANOVA, and ANOVA is the recommended technique now in AIAG. Watch the appraisers measure the samples. Don't just hand them the parts and hand them the gauge and walk away and come back and get data. Because if it fails, you won't know what caused the problem. You won't have any of the within or between information that will help you resolve the problem. So how do you know the measurement technique is good enough to make good data and therefore good process adjustment decisions? Well, if you take a look at the measurement errors, you have Gage R&R, which is the reproducibility plus the repeatability. The Gage R&R plus bias gives you your gauge capability, and then your overall gauge performance is a gauge capability, which is your bias and your Gage R&R, plus stability over time and consistency from usage to usage. So again, to be acceptable, you take a look at the location error. In general, the bias or linear error of a measurement system is unacceptable if it is significantly different than 0. That means when you calibrate it, it should be measuring that value. Or if it exceeds the maximum permissible error established in the gauge calibration procedure. So if you have gauge blocks and you're using those as the standard and the measurement gives you within its resolution 1 or 2 data points, and that's what you say is acceptable, and that much variation will allow you to pass Gage R&R, then that is what you're going to use, and that's all part of your calibration records. Then you have to take a look at the width error. The criteria as to whether measurement systems variability is satisfactory are dependent upon the percentage of manufacturing production process variability or the part tolerance consumed by the measurement system variation. This is key because when you're looking at your Gage R&R data, when do you use percent process variability? When do you use percent part tolerance? They're used at 2 different times, so one's not better than the other, and you don't necessarily use both at the same time. If the gauge is the final acceptance criteria for a specific measurement system, depends on the measurement's environment, purpose, and should be agreed upon by the customer. So let's take a look at a typical report. Assess the variation for each source of measurement error. So you use the variance components var comp and percent contribution to assess the variation for each source of the measurement error if you're using, and for example, this is Minitab. So you see the var comp down there, which is the component variation. The first line is the total Gage R&R. It is a sum of the repeatability and reproducibility variance components. So your total Gage R&R in this particular case, 0.00200816 or 6.82% contribution. The next thing you look at is your repeatability and reproducibility. Repeatability, again, the variability of the measurements are the same operator measures the same part multiple times, and the reproducibility is a variation between the operators. In this particular case, very similar, so it's be difficult to tell if one was a problem versus the other. Then you take a look at part to part. That is the variability in the measurements due to the different parts. Ideally, very little of the variability should be due to the reproducibility and repeatability. The differences between the parts should account for most of the variability. This means it can tell the parts apart, and it can do so with very little error. When the percent contribution from part-to-part variation is high, the measurement system can reliably distinguish between the parts. And again, I mentioned earlier, you have to present parts that can tell it apart, or you're not going to pass your Gage R&R. Use the percent study variation or percent study var to compare the measurement system variation to the total variation. The percent study var uses the process variation as defined by 6 times the process standard deviation. So the percent study variation is the 6 times the standard deviation of what has been supplied to the study. Then you have the percent tolerance column, and that's where you find if you're going to use that gauge to tell parts that are good or bad, for example, a final inspection, you're not going to use it to make decisions on the process, just whether or not they're good or bad. Then you use the percent tolerance. The width error for measurement systems whose purpose is to analyze a process. A general rule of thumb is the measurement system acceptability is under 10% total gauge R&R is considered acceptable. 10 to 30 may be acceptable depending on the importance, cost of the device, and cost of repair. Over 30 should be considered not acceptable. Every effort should be made to improve the measurement system. Once again, and this is key, percent tolerance is used for gauges used to qualify product quality, such as final inspection. Percent process variation or percent study variation is used for gauges used for process control, especially SPC. If you met your gauge acceptance requirements and you are under 10%, for example, you're done. You have a great gauge. You have a great day. Unfortunately, that's not always the case. So what do you do if you fail a gauge R&R? The following supplemental data helps you analyze the gauge problems. So here's your gauge R&R, X-bar and R for response. The components of variation graph. The components of variation graph show the variation from the sources of the measurement error. And here you're looking at percent contribution, percent study variance, and percent tolerance. Mini-tab displays bars for percent tolerance when you enter a tolerance value. If you don't enter a tolerance value, you're not going to get it. And the mini-tab displays bars for percent process when you enter a historical standard deviation. And that's your best information, is the percent process. The graph shows part-to-part variability is higher than the variability from repeatability and reproducibility, but the total gauge R&R variation is higher than 10% and might be unacceptable. The gauge R&R graphs provide information about the measurement system. So it shows whether the largest of the component variation is part-to-part variation. In an acceptable measurement system, the largest component of the variation is the part-to-part. The R chart by operator shows whether if any points fall above the upper control limit. If the operators measure consistently, the points will fall within the control limits. So on this, and this is key because it doesn't always work that way when you're using these charts. For the R chart by the operator, if you fall outside the control limits, then you're having too much variation within the operator. The X bar chart by operator shows whether most points fall beyond the control limits. The parts that you choose for a gauge R&R study should represent typical part-to-part variability. Thus, there should be enough variation that you can tell them apart. If you can't tell them apart, then they're going to fall within the control limits. And the graph should show that most of the points fall beyond the control limits for you to be successful. So if you failed your gauge R&R and your X bar chart by operator falls within your control limits, what it's telling you is that the gauge cannot tell those parts apart. So either your parts don't show enough variation to represent the variation over time, or your gauge can't tell them apart, and the gauge is not a good gauge for the process. Measurements by part graph up on the right, top right, show whether multiple measurements for each part are close together, which you would assume they should be. Multiple measurements for each part that are close together indicate small variation between the measurements of the same part. What's interesting about this is sometimes you'll find a part that has a wide spread. It's probably going to be creating problems with your gauge R&R, and you may want to go back to that part and find out, why does that gauge have so much variation with that particular part? Is there a surface condition? Is there a taper? Is it difficult to hold? What is different between that part and the ones that are measuring well? That's a key investigation you can have if you see that issue in that particular chart. Measurements by operator graph shows whether differences between operators are small between the differences in the part. A straight horizontal line across operators indicates that the mean measurements for each operator are similar. That's a good sign. Otherwise, if it's not straight, then you have somebody measuring smaller than another, so on and so forth. The measurements for each operator vary an equal amount looking at the bar. Then there's an operator part interaction graph. shows whether the lines that connect the measurements from each operator are similar or whether the lines cross each other. Lines that are coincident indicate that the operators measure similarly. Lines that are not parallel or across indicate that the operator's ability to measure a part consistently depends on which part is being measured. Another thing that you can look at in the operator influence is if you have one operator that has more variation than others. I had a situation where we had 3 operators using a gauge, and one operator had significantly more variation than the others. I went back to investigate what was happening with that particular operator and found out that that particular operator has headaches and was using Excedrin, which is contains caffeine, and she was actually shaking enough to create more error in that particular gauge. So there was a significant operator influence on that particular gauge. A line that is consistently higher or lower than others indicates an operator has bias to the measurement by consistently measuring high or low. So that's another very good chart to take a look at if you failed your Gage R&R. Again, if you pass, none of this stuff is really important because it should all be fine. This is what you do when you're analyzing failed Gage R&R. Unilateral tolerance. So what is percent tolerance? When a process has 2 specification limits, the tolerance equals the difference between them. And the percent tolerance equals the study variation of a given variation source divided by this tolerance. However, this method is invalid when you provide a single specification limit. So if you have a max or a min, how do you deal with the acceptability criteria? The example of processes with 1 specification limit, many processes operate with 1 specification limit, such as a min or max, such as a lumber mill cuts beams to a perfectly straight, but beams frequently warp during manufacture. Measurements of the warping have an upper specification limit to distinguish acceptable and not acceptable degrees of warping. However, these measurements have no lower specification because they cannot take values less than 0. In fact, 0 represents a perfectly straight beam with no warping. In addition, some processes have a lower specification but no upper specification limit. For example, a cutlery manufacturer must verify the hardness of its knife blades is higher than 55 on the Rockwell C scale. The lower specification is 55, but no upper specification limit exists. So if you're looking at percent tolerance, how can you do that if you don't have an upper and lower tolerance? How does Minitab calculate percent tolerance when I enter a one-sided tolerance? Minitab calculates a one-sided process variation by dividing the study variation statistic by 2. It defines a one-sided tolerance as the absolute value of the difference between the single specification limit and the mean value of all measurements. It calculates the percent tolerance statistic by dividing the one-sided process variation by the one-sided tolerance. How do you handle automated test stations when there's no operators? There's several options. One is to use specific nests or fixtures as operators. That's handy if you have rotary tables, especially if the nest or fixture is a part of the measurement system, such as it's holding the part by its datum. Another is to use a time order as an operator. So if there's no nest, or there's only one nest or fixture, there's no operator interaction, then the good idea is to run 10 parts 3 times, then run 10 parts 3 more times later, and then run the same 10 parts 3 more times later than that. What that will do is give you an idea of whether that machine operates consistently over time, and oftentimes you'll find some amazing results from attempting to do that, especially if you do one during the day and one during the night, and there's any temperature differentials or humidity differentials between those periods of time. Using time as an operator, you can look for stability issues over time that the trial was performed. So in this case, we do it 3 different times, and Was it getting better? Was it getting worse? Was it getting higher? Was it getting smaller? Those are the types of things that you can see, and it gives you value on the study rather than just running 10 parts and giving up, or running 10 parts 9 times and giving up and reporting whatever you get. At least it gives you an idea. Is that machine really working the same over a day or maybe even a longer period of time if that's of interest? Now, a lot of people don't really understand NDC, although NDC is a very powerful tool. It's the number of discriminant categories. It's extremely powerful when you're trying to do SPC. So what is number of distinct categories? The number of distinct categories is a metric used in Gage R&R studies to identify a measurement system's ability to detect a difference in the measured characteristic. The number of distinct categories represents the number of non-overlapping confidence intervals that span the range of production variation. The number of distinct categories also represents the number of groups within your process data that your measurement system can discern. Let me boil it down to this. It is your statistical resolution. If you have 10, an NDC of 10, that means statistically you can have 10 buckets that you can tell apart within your process variation. If you have 3, for example, or 4, then you probably have statistically the amount of confidence in that data as using a gas gauge in your car, which is not very impressive. Which, in fact, if you're doing SPC, you should have an NDC of 10 at a minimum, and the requirement of having an NDC of 5 is woefully inadequate for SPC. Minitab calculates the number of distinct categories by dividing the standard deviation for the parts presented by the standard deviation for the gauge, then it multiplies it by 1.41, which is its square root of 2. So the number of categories that are calculated depends on the ratio of the variability in the measured parts, which is the variation that was presented to the study, and the variability in the measurement system. Again, this isn't used in tolerance at all. This is only used for process variation, and it only understands the process variation that was presented to it in those parts, unless you use the option of using the historical standard deviation. AIAG recommends that 5 or more categories indicates an acceptable measurement system. And then here's some ideas. If it's less than 2, then there's really, you can't tell the parts apart with it. That's why it's not a good choice. When it's 2, you can take your parts and split them into 2 discernible groups. If it's 3, you can take your parts and discern them into 3, and so on and so forth. But as you can tell, that's not very impressive when you're trying to make decisions on your process based on the process variation that the gauge can accurately discriminate in. And here's another example. 1 data category, it's either in or out. Not very impressive. 2 to 4, still not very much resolution. 5 or more, I recommend 10 to have enough variation that you can tell what's going on within your process variation. And your process variation, if you think in terms of SPC, is that which you have within your control limits, because they were developed by determining what your expected process variation is going to be over time. So once again, if you measure 10 different parts and it reports the number as distinct categories as 4, that means your measurement system can detect the difference between only some of the parts. And increasing the precision of the gauge will increase the number of distinct categories. Again, when doing SPC, if you have too few distinct categories, you're going to get chunky data, and it's not going to give you enough time to make decisions when you need to make an adjustment. It will cause your decisions to be inaccurate, possibly cause the operator to make decisions too late, causing the process to make out of specification parts if it's too small. You should actually have, again, an NDC of 10 if you're charting. Now take a look at this data here. If you look at the resolution of the yellow dots, that would be very similar if you had 5. According to this, looks like it's doing fantastic. Now with more resolution, you can see that it actually, that process is trending downwards. That is why it is so important to have the resolution when you're doing charting. And the NDC, and what I'm referring to here is actually the NDS, the number of discriminant samples. If you don't have enough samples, and you don't have enough discrimination in your gauging, neither one of your charts are going to be accurate enough to make good decisions. So number of discriminant samples, having good gauging system has no value if your sampling rate is too slow or too infrequent. You should have sampling rate of at least 5 points between process activities. So if you're doing offsets, if you're doing any type of adjustment, you should have at least 5 points. Same reason why you have at least 5 categories in NDC, or you're going to be wasting your gauge accuracy. In fact, you're probably going to be wasting your time. Whew, I think we made it. If you have any questions, you can turn on your mics now. And anyone? All right, well, if there's no question, oh, here's one. And then I'm going to say, well, here comes the question. Let me run back up in there. And I'm going to say, how is the best order to do it in terms of calibration, linearity, stability? Calibration is number one. You got to make sure that it's actually measuring correctly before you even start on that. As a part of calibration, you do linearity. You want to make sure that that gauge is measuring throughout its range correctly. So those two are tied together. You won't have stability until after you've used that gauge over a period of time. So the Gage R&R will come right after calibration and linearity. Stability will come last. Hope you got that one, Ben. Anyone else? You can type in the chat if you want. I hope this has been helpful. All right, thanks everybody. I'll stay on for a couple of minutes in case you come up with any questions. You can type them in there. Other than that, I hope you have a great day. Good luck. Have fun with your gauges. Okay, the question is how to ensure if parts are dissimilar when you're doing Gage R&R and destructive methods. That is a real challenge. AIAG has presented some options of using parts off of different processes, but oftentimes you don't have different processes. One of the things I did, and it may not help everybody, I'm sure, is I had a situation where I had to do a peel test on a weld, very, very small weld. It fell within 15 pounds pull. So what I did, and this is just a suggestion, maybe you can extrapolate from that. I got fishing line and I used it as a surrogate to determine whether it could tell apart. So I got monofilament fishing line, which is very consistent. And I used 2, 4, 6, 8, 10, 12, and I used those as the samples. And then each one, of course, was destroyed, but I could tell apart the 2, 4, 6, 8 pound samples. And that worked out very well for trying to determine that type of Gage R&R for that test. Sometimes you'll have to use surrogate information because you simply cannot find that much variation in your part. If you're, let's say you're doing destructive pull testing on steel, you may have to turn a couple down in order to have less, but have them turned down like barbelled so that it's very consistent within those groups. But destructive method, probably could do a whole presentation on the whole thing because it's extremely difficult to sort through destructive methods because of the sample. Most of Gage R&R issues go back to the samples. Then after that, it's a matter of, are you paying attention so you can determine what went wrong if you failed. But the samples are your biggest problem. Okay, comment on creating part samples for the study. Your biggest problem when you're doing a Gage R&R, you just bought the gauge and you're just starting up a new process. So where's the variation? One of the things that you need to do is understand that when you first start a process, you do maybe a PPAP run of 300 parts, you're not going to have very much variation. That it's not going to represent what you're going to see over the life of the part. So what you may have to do is actually alter those parts to have the variation that you will see over that period of time. That's one technique. The other is you might be able to estimate that variation. You still have to have parts that you can tell apart. And generally, when you, if your process isn't making very much variation from the very beginning, you're going to have to alter them. The other thing you can do is over time, if you're doing a new gauge on a process that's been around, is save parts from different lots. Collect parts that have that variation. If you have tool wear, for example, grab some parts at the beginning of the tool and parts right before you change the tool, then collect those types of things. But again, the hardest part of all of Gage R&R is trying to get these samples that represent them. Some people will drop in all kinds of variation. If you throw in parts that are out of spec, you will see that error on your report because your PV, your percent process variation, will be smaller than your percent tolerance. What that says is that you expect your process to run out of spec a lot. That's not what you want for your process variation. So throwing in parts that are out of tolerance will give you parts that you are able to see the difference in, but it's not going to be representative of the process. It's going to give you a false Gage R&R. Now you can use those parts if you have the historical standard deviation and plug that in, because then it will use that variation for your process variation far, far more accurate than anything that you can present in part samples. Hope that helped. Like I say, that's one of the toughest parts. If you don't have a spec at all, for example, a legacy product, and you want to start measuring a particular characteristic using your test method, what acceptance criteria do you use? If you don't have a spec, then you're really left to testing it versus your process variation. All you can do is say, okay, here's my process variation. Can I use this to control the process within the variation that I'm going to say? That's all the tool can do. It can either compare it to a spec or compare it to a process variation. There really is no other thing. And within that, then you would still use your 10% or your 10 to 30% being questionable and over 30 being unusable. So but that's all you're going to have to use in that particular situation. Or the other thing you can do is generate a process spec. What is the variation that if you exceed that variation is going to create a problem either in further processing or in use? But if you don't have that, then you would have to use your process variation. Any other questions? All right, well, I'm going to try to pass this ball back to Norval.